right. So my name's Avery Archer. I'm a professor here in the Physics and Astronomy department, and also an alumni here at DePauw University. I graduated in 2011. I have a specialty in very high energy astrophysics. That's my main area of study. And today we're going to talk a little bit about the eclipse that we had back in the beginning of April and why eclipses are so interesting despite how simple they are. So oftentimes as an astronomer we get questions, especially leading up to the eclipse, about why do we care so much about these things, right? And people want to understand how an eclipse actually works. And originally I was asked to give a talk about the basic physics of an eclipse, and was suggested that that would be an incredibly short talk because the underlying physics of an eclipse is it takes about a minute to explain what's happening. I've got some bright light shining on me right now. An eclipse is just this, holding my hand in front of the light, right? And it's casting a shadow on my face. And that's really all that happens during an eclipse, except for it's the moon instead of my hand, the sun instead of the lights. So that's it. That's all we've got as far as the basics of an eclipse. And obviously that doesn't make for a very long talk. And so what we're going to talk about here is a little bit more of why these things are so fascinating to folks, why we make such a big deal out of what is such a simple phenomenon. And we can see historically that this is not a new thing, people being fascinated by eclipse. There are historical accounts of eclipses, basically going back as far as we have written history, with folks talking about, in some way, shape, or form, how amazing these eclipse phenomena were. And typically, before there was a good scientific understanding of what was happening with an eclipse, these descriptions always invoked the supernatural, right? And oftentimes, unpleasant supernatural things, right? The gods are angry, things like that. There are many instances, descriptions of mythical creatures consuming the sun before we had a good understanding. It's just the moon blocking the sun's light. There's a myth of poison falling from the sky during an eclipse, angry gods making night of the daytime, all sorts of sort of apocalyptic type descriptions, scenery, things like that. So they're really spectacular events, which is why there is so much build up to this event, especially because we were able to be in the path of totality here on campus. Many religious texts make some sort of reference to eclipses or eclipse-like events, that whole idea of the daytime becoming dark, very unnatural seeming thing, despite it actually being a really simple natural phenomenon that takes place. So this first image here that we have is a pretty straightforward depiction of what an eclipse is. This is a photograph actually from the 2017 eclipse. And you can see how spectacular it looks. We'll talk a little bit later about what you're actually seeing in this image. But this sort of gives you an idea of the visual, how spectacular this can be. Right, again, an eclipse is just a shadow, and so we want to get a good sense of why we make such a big deal out of these things. So to get into some more specifics, the oldest recorded eclipse was in 3340 BCE. This was recorded on rock carvings in Ireland, and that's the first recording we have of an eclipse, right? So we've known about them, we've experienced them for a long time. In 1200 BC, there was an eclipse in China. The written description then was the sun has been eaten. That was the quote that was given. Again, sort of telling us how spectacular these things are for folks that have witnessed them. And then there's at least one historical example where two astronomers were actually beheaded because they weren't able to correctly predict an eclipse. Thankfully, I don't think we do that anymore. We had a very good prediction for this year's eclipse. We all get to keep our heads, so that's no longer an issue. But again, because of how really outstanding and magnificent these phenomena were, and the association with the supernatural, we see sort of these extremes associated with them, where rulers wanted to know when things like this are happening, because at the time there was some implication that there's favor or disfavor with the gods if these sort of things were happening. Fortunately, now we can predict eclipses hundreds of years out, and so it's not just a rough guess of when they'll happen. We have very accurate predictions of when they'll happen, the nature of the eclipse, where it will be, the exact path, all of these things. Because again, we'll talk about some of those detailed physics, but the physics of it is fairly simple. But again, still want to get a good sense of why it's a big deal. Right? I've mentioned several examples showing that historically people have viewed them as a big deal, but why? And I think part of understanding that is getting to see it. Right, so we've got this one picture from NASA for it. Here is another image. This is a composite image, so it's a series of photographs that were taken during the 2017 eclipse. So an eclipse does not actually make the sun show up in the sky multiple times like this. This is just showing the progression of the eclipse from start to finish, where you can see the sun slowly being covered up by the moon, that moment of totality in the center there. And I also like this photograph because it gives a sense of how dark it gets during a total eclipse, right? Because many people have experienced a partial eclipse and maybe you went outside and looked at it, but if you weren't in the path of totality, probably did not hear near as much in the news and just about every source of information as you would have leading up to the eclipse that we had this year, because there is a pretty spectacular difference between a partial and a total eclipse. So yeah, there are multiple things that are depicted here, getting to see that transition and what that looks like altogether, but also getting a sense of just how dark the daytime sky will be. Because keep in mind, this looks like it's about twilight, late in the day, middle of the summer, so maybe like 9, 10 o'clock, something like that. This is what the sky looked like at 3 p.m. on campus, right? So again, it's a very spectacular event. It feels very unnatural. I don't want to say it is unnatural because, again, it is a very basic natural phenomena that we see take place. And part of why there's so much sense of awe and wonder around these is the sun being out in the daytime sky and providing light during the day is one of the most predictable things that we have, right? The sun always rises in the east, sets in the west every single day. And so if you can put yourself into a place where you're imagining a time where you don't know what's causing an eclipse, and then all of a sudden in the middle of the day, it gets dark, twilight level dark. How bizarre would that be? Right? It's a very strange phenomenon to happen in the middle of the day if you have no context or understanding of what's happening. Fortunately for us, we have good predictions. We all knew this was coming, had our eclipse glasses, things like that. But especially if you somehow were to avoid all that, what a strange thing to observe in the middle of the day. And it's not hard to imagine, or at least start to imagine, why, without a physical understanding of what's happening, that this event you might give credit to these events to some sort of divine presence, right, or some sort of supernatural actors, right? Another view that I really like and I think impresses the spectacular nature of this event comes from a series of NOAA satellite images, right? So here we have just a picture of Earth, right? During a normal day. It happens to be from 2017 when we had the previous eclipse, right? This is the Earth polychromatic imaging camera. It's there mostly to observe weather patterns, things like that. And the interesting thing about the satellite is they take pictures every so often, so you can actually see from outer space the progression of the eclipse. And we move through one image at a time. It looks like a normal day here, some cloud cover, right? And then in the upper left, you can start to see a very dark shadow. And as we progress through this, you can see that dark shadow move across the face of the globe, right there over across North America, moving. Of course, the Earth is spinning at the same time, and you just see this black shadow pass across the face of the Earth until it's gone. And that is a view of an eclipse from outer space. But if we go back to an image here where we can see that shadow, I think this impresses the spectacular nature of it. This looks like something you might see in a movie about the apocalypse, right? There's some really dark shadow cast over a large portion of the face of the Earth. And again, really all you're seeing is the moon shadow. So in some sense, it's a really spectacular thing to witness, but also it's kind of like holding my hand up in front of the light. It's a shadow, right? That's it. That's all there is. So we have this interesting balance of it being such a simple thing, but really being a spectacular thing to witness, right? Without the context, knowing this was an eclipse, if I were to show this to you, you probably come up with some very interesting ideas of what on earth would cause this dark patch over a significant portion of the face of the Earth, right? So again, is a very strange thing, very weird to see that. We're going to talk a little bit about what exactly an eclipse is, a little bit more detail than just sort of the hand in front of the light model. So what we have here is a cartoon version of the sun, earth, and moon system, right? So things are not to scale here, anything like that, but it gives a rough sense of what we're seeing, right? We've got the sun out at the far edge, we've got the moon, and then planet Earth, right? And in this cartoon version, and more or less what happens is the moon goes around the Earth, right? It's orbiting around our planet. It takes about 27-ish days to orbit. That's where we get the moon phases and cycle of the moon. That would be a topic for another time to go through. But every so often, the moon actually passes between the Earth and the sun, right? And this is the new moon phase, which is being depicted there, right? If you were to look at the moon, it would be difficult to see because you don't have that illumination from the sun. So to get a sense of what happens during an eclipse, we follow rays of light coming from the sun to see exactly what happens. And that's what we're seeing with those white lines that are depicted in the image. We're following a couple rays of light from the edges of the sun to see where they land on Earth. So if we do that, we can see that first, not all of the light from the sun is blocked from Earth, right? Which is certainly what we witness during an eclipse. And we also see a pattern show up in the shadow where you sort of have this narrow cone that's a darker part, and then we have the sort of wider cone, which is still in a shadow, but not nearly as dark. And these are two different parts of the shadow that we call the umbra and the penumbra. So one being darker than the other. So that broader part, the penumbra, is the part where you would see or witness a partial eclipse. And the penumbra, that would be that path of totality that passed across North America and through Greencastle. It's that darkest part where the sun is essentially completely blocked by the moon, right? So this is how we get a total eclipse. Right? And I said the moon passes by, orbits roughly 27-ish days, but we don't have a total eclipse on Earth every 27 days. Right? So the natural question would be, well, why don't we? So I said it's a fairly simple phenomenon that's going on. It's actually just a tiny bit more complicated than what's happening here. If this cartoon version were completely accurate, we would have a total eclipse every 27 or so days. But it turns out that slight complication is that there is a tilt here, go to this next slide, to the moon's orbit. So it's not going to be the case that every time the moon passes between the sun and Earth, that it is directly in between the sun and Earth. And that's what's being shown here, is that shadow from the moon actually isn't being cast on Earth, but is just kind of out in space. And that's what happens most of the time, right? It's actually only occasionally that the moon is in the right position as it's going through that orbit to cast that shadow directly on Earth to give us a total eclipse, which is why they're not terribly common a phenomenon. Right? And there are additional complications to it as well. Right? The Earth's rotating at the same time, and so we don't have that eclipse phenomena always happen in the exact same place. And we can see that from this next image here, where this is, of course, a map of the globe showing eclipses over a range of time. This is, let's see, for the eclipses that'll happen in about the next 7 years. And you see that they're all over the place in the globe. And again, that just has to do with the detailed complications of that Earth spinning, the moon orbiting, and where exactly that shadow is going to be cast. But it's not an incredibly rare phenomenon to have an eclipse. We tend to have roughly 2 to 3 eclipses per year, with around 2 total solar eclipses roughly every 3 years. But for any one location on Earth, they are incredibly rare because of those complications of the spin of the Earth and the moon's orbit. So the last one in Greencastle before this year was over 100 years ago. The next one in the United States will be in 2044, and the next one in Greencastle won't be until 2153. So this is really part of why people make such a big deal out of them, because unless you make it a point to travel to see an eclipse, it's incredibly rare to see one in any one particular location, which is actually what made it so spectacular that we had one in 2017 in the U.S., and then one this year in the U.S. We don't often have them that close to each other. The other thing that's really interesting, going back to this image showing the umbra and the penumbra, that region for the total eclipse is not a very large region. It's only about 50 miles wide on Earth. And so that path of totality is fairly narrow, which is what makes it particularly exciting to be within that path, because there's a spectacular difference in what you see for a partial eclipse versus a total eclipse. So to talk about the three different types of eclipses that we can have on Earth, here we have a basic image of those three. We've got the total eclipse on the far left, an annular eclipse in the middle, and a partial eclipse on the far right. Partial eclipse is the most common. The moon is simply covering a part of the face of the sun. And so it gets a little bit darker, but not terribly noticeable unless it's a high level percent of coverage, right? And so we were able to witness at least part of that, the progression of that during the total eclipse, right? So it can be very interesting to see this happen, but not quite as spectacular as a total eclipse. In fact, there was an American astronomer, J. Pasachoff, that said, seeing a partial eclipse and saying you've seen an eclipse is like standing outside an opera house and saying you've seen the opera. In both cases, you've missed the main event, which, especially having seen the eclipse this past year, I can absolutely vouch for that. There's a tremendous difference between seeing that partial covering of the face of the sun versus the moment of totality. So again, what's happening is we've got the moon slowly covering the face of the sun bit by bit, nothing terribly complicated. As we move towards a total eclipse, what's happening is you start off with something like this. The moon passes over the face of the sun, covering more and more. And then we have a couple different phases that are worth pointing out. The first is this stage that's shown here where the sun is mostly covered up, not entirely, and you see a couple bright spots on the edges. And these are called Bailey's beads, named after Francis Bailey, who had an explanation for them back in 1836. And we only see a few bright spots, and these I think are really interesting because what you're seeing is just a couple places where the face of the sun, the photosphere, that outside shell, is still shining through valleys on the moon's surface. Right? The moon is not perfectly flat. If it was perfectly flat, we wouldn't see these tiny beads towards the end, right? You'd see just a smooth surface. But because it's not perfectly flat, we have these valleys. What you're seeing is that topology of the moon, right? You're seeing where some of those valleys are located, which I think is really fascinating. And then the very last moment before totality is the diamond ring. This is the last valley on the moon, wherever it happens to be, depending on some of those dynamics of the moon-Earth system, before the sun is completely covered. So that's that last little bit of light coming from the photosphere. And it seems brighter here. That's an effect from a camera, but it is very interesting to witness this. And then once the moon moves just a tiny bit more to completely cover the face of the sun, we have that moment of totality. Right? The sun is completely covered up, or at least the photosphere is, and what we can see now is the corona. Right? So that's these sort of fringes, the sort of a filamentary structure look to it. This is really the upper atmosphere of the sun. It's something that is always present, but it's fairly dim compared to the face of the sun, and so it gets completely washed out if you were to try and view the sun, even safely using proper filters. You wouldn't see very easily the corona, right? Because that face of the sun is so incredibly bright. And the corona itself is really interesting to see. You see these filaments, or what are called prominences. This is plasma from the sun extending out of the surface of the sun out into that outer atmosphere. And without going into too much detail, it's indicative of the magnetic field structure of the sun. And the plasma sort of follows the magnetic field lines. And what's really spectacular, in my opinion, besides just the visual itself, is to think about the scale of this. Right, that those filaments that we may see here look relatively small, but you have to keep in mind the scale of the sun, that even small filaments are the size, many times the size of our planet in a lot of cases, right? It's also interesting being able to view the corona for scientific purposes because it's a different portion of the sun. Right? It's dimmer, and we can get a better sense of details of how the sun functions by viewing these parts. There's actually observations in 1868 viewing the corona of the sun that the element helium was discovered. right? There was an astronomer, Pierre Janssen, that was studying these solar prominences, trying to understand some details of them, and he was using a device that at the time was fairly new called a spectroscope. And a spectroscope essentially takes the different colors of light and splits them up into their individual colors, their individual energies. And it was known at the time that different elements had unique signatures in the spectra that they showed. So you could identify elements from some light source by looking at them through a spectroscope, seeing what distinct colors of light you would see. They serve as sort of like a fingerprint for different elements. They're unique to each element and molecule. And we, at the time, knew of many different elements in the table of elements. And so Pierre Janssen, in studying the corona here, was looking at that set of spectral lines, and he noticed one line in particular that didn't correlate with any known substance. It was a very bright yellow line that was close to the element sodium. Sodium has a yellow line, but it wasn't quite the right color of yellow. And after some follow-up studies, it was determined that was a unique line, that there was a previously undiscovered element that they were seeing in these observations. And of course, the Greek word for sun is helios, so we call that element helium now. So there's lots of interesting physics that we can get from studying solar eclipses, because that brightest part of the sun is covered up. Right? So the other thing that's worth talking about is just the path that this particular eclipse followed. You can see it here on the map, showing the path of totality, moving from the south in Texas up across the state of Indiana, in particular Greencastle, showing all the times and stuff. So, prior to this event, people could get prepared, know where to be. Of course, we were well prepared on campus with our solar eclipse glasses, and had a great chance to witness this event, get to see some of these spectacular views, and get a good sense of that sense of awe and wonder that there was a lot of talk about, and some people were unsure whether it really would be that spectacular or not. But we have some photos from the day in the physics department. We were getting set up. We had several telescopes that we were able to set up on campus. We were taking a look at our telescopes, getting them prepared to go set them out in Bowman Park and a couple other places so that folks could view the eclipse safely. This is a view from where I was at, just outside Bowman Park, and you see this was early on in the eclipse, people sort of getting settled. So we had a really great turnout on campus for this event. The telescope I had set up here had a nice projection of the sun, so you could see that eclipse, the partial eclipse as it was passing over. You could actually even identify some sunspots on that projection. We've got one of our physics majors here sort of toying around with that projection. And folks viewing the eclipse with some solar binoculars to look more directly at it safely. So it was a really great time on campus, and hopefully this gives you some sense, if you weren't able to see the eclipse itself, why it's such a spectacular event, why we make such a big deal out of it. There's a lot more physics that you could talk about associated with eclipses, but there's only so much that we want to do at one time. So hopefully this gives you a good sense of the spectacular nature of these things, why they're really magnificent, even just to witness before you get into all the detailed physics of what happens during an eclipse. So thank you very much. Next, we're going to have Dr. Howard Brooks talk a little bit about eclipses as well. He's another faculty member in the Physics and Astronomy department, and I'll turn it over to him.
Well, thank you, Avery. And I'm going to focus on one particular learning experience we had through eclipses that relates to the basic concept of gravity, or the contrasting view that was presented by Einstein a little over a century ago that involved the idea of warped space and the general equivalence principle, or general relativity, and use the solar eclipse observations as a way to get into that. And the first caveat is nature does what nature does. Okay? And all we're trying to do sometimes in physics in particular is trying to explain what nature does in a way that we can then make predictions and we can follow along and have a good idea of understanding why nature does what it does, but we don't always get to the exact precise answers. And of course, one concept that's been known since the beginning of time is what we wound up recognizing is the thing that things fall towards the earth. You drop something, it goes towards the earth. And this has been known to the ancients as well as to modern-day people, and we're all aware of things falling, including ourselves sometimes. Aristotle was of the opinion that it was a natural tendency for objects out in the environment to go towards what we believed to be at that time the center of everything, which was the center of the earth. And he also believed that more massive objects would fall faster. He was right about the idea of objects tending to want to fall towards the surface of the earth. However, he had some problems that heavier things, more massive things did not necessarily fall faster, and that's what we give Galileo credit for the Tower of Pisa and dropping different mass balls off the tower and having them fall to the ground at the same rate and reach the ground at the same time. Perhaps some of you recall the famous experiment with Alan Shepard on Apollo 14, where he dropped a hammer and a feather on the moon to really prove it dramatically about the nature of gravity to do that. Newton, about 50 years later, came up with a mathematical model for gravity, and that model was based on some very simple ideas. It was based on the idea that masses attract each other, and more mass meant a stronger attraction, and the acceleration that you experienced depends on the concept of what he called force, like gravitational attraction, and mass. And so when you have something near the Earth that's being attracted to the Earth, they both want to fall towards each other, but the small mass object does the major acceleration, and the larger mass object hardly even notices that. And so Newtonian gravity had a lot of interesting implications, and it gave an answer to another set of speculation that occurred at the beginning of the 17th century, dealing with the ideas of Kepler, who had some laws of planetary motion, how objects went around the sun. And those laws were great, but there was no explanation for them until Newtonian gravity came along and explained why planets move faster when they're closer to the sun, why planets that are more distant from the sun travel slower than the ones that are closer, and the various basic principles that are in Kepler's laws of planetary motion. However, by the 19th century, so a couple of centuries later, of the known planets, Mercury and Uranus were both not following Kepler's laws. They were not moving quite as would be expected or predicted by Kepler's laws, and under that, the Newtonian concept of gravity. And that led very quickly in the mid-1840s to the discovery of the planet Neptune. The scholars looked at the data and said, well, if there was another planet that Uranus had been passing in front of, because it would go around faster than this more distant planet, then Neptune would first pull it faster and then slow it down. And that worked out beautifully. It was a perfect prediction for where to find Neptune, and it was found literally on the first night of observation efforts to see the discovery of Neptune. And however, the idea of a planet being inside Mercury's orbit to cause Mercury's orbit to shift its closest point to the sun more rapidly than what Newton would account for led to the search for a planet that was known in the 1800s as Vulcan. This was going to be just a cute name for a planet because it was going to be so close to the sun that seemed like an appropriate god to pick for the planet. And so in the 19th century, it was very difficult to see planets near the sun. It's still hard for us. Many people have never seen Mercury because it's so close to the sun most of the time. So in order to try to see planets near the sun, there was the idea by the Lick Observatory out in California to go to solar eclipses around the world and try to get photographs during the eclipse sun that would still show Vulcan, because all planets reflect starlight, they reflect sunlight in our system, and they would then be an opportunity for us to see this planet that's so close to the sun and be lost in the solar glare to speak of. And so that's what Lick wanted to do as an observatory. And so they set up a whole series of expeditions. This graphic was taken from an article that was focusing on the 1898 eclipse path, which went through Johor in India. But you'll notice there just a steady stream from 1889 through actually 1922, where they went on various solar eclipse exhibitions. And some of them had some fair success. Others didn't. You'll notice, as Avery made a comment about earlier, sometimes you get two eclipses in the same year. So there's a pair of them from 1889 that they were able to observe. And so we're going to talk a little bit more about the 1914. Then we'll get to the the 1919 eclipse, which Lick did not go to, and we'll talk about why that happened. And then we should, at the end, give credit to them for the 1922 eclipse that went through Walai in the western portion of Australia. Okay. So, independent of this search for Vulcan, Einstein was troubled by the, I'll say, the action at a distance, the immediacy of two objects far, far apart having an influence on each other. And so he was trying to come up with a different scheme of how things might be explained, and got to the idea that if you were in absolute free fall, you would not be able to tell the difference between that and an object that was moving under the influence of the warp of space by another more massive object. And he called this work the general equivalence principle. It followed his special relativity, which had been proposed in 1905 and well accepted. And so he was working on that, and so his model is very mathematically involved. And I'm not going to deal anything with the math here today, but he wound up saying that there were 4 dimensions to worry about: left, right, front, back, up, down, as well as what was called space-time. Space-time was a product of time, as we might think of it, and the speed of light, and it allows for recognizing that certain objects would influence others, but some objects would be located at locations within the universe where they could never know that the other object was there, and that eliminated this idea of needing to worry about the action at the distance between two masses that was in Newton's work. And mass would warp the shape of the space. And here's a simple graphic, courtesy of the European Space Agency, showing the idea that different masses, we've got a yellow mass, sort of a copper-colored mass, and a red mass, warp space. The more the mass, the more the warping, the more the bending of these lines. And so objects that were traveling through this space would follow what they thought was a straight line, but it would actually be a curve. I guess a modern equivalence that we could think of to that is the idea of just walking on one of our latitude lines in the Earth. We're close to 40 degrees north latitude here. If we just walk along the 40th degree north latitude, we think we're walking a straight line. But if someone were to view us from above, they would see that we're going around the surface of the Earth. And so it's this warping idea that could also be tested during solar eclipses. And so, so what it amounts to, and here this graphic shows it a little bit better, a star, which is located here almost behind the sun, would be bent as it passed nearby the sun, and our eye would perceive it down here in the lower right. And we always think light travels straight lines, so we would think the star would appear to be much farther away from the sun than where it actually is located. This is the same thing that might happen if you've ever been in a swimming pool and looking down through the water at something on the floor of the swimming pool, and it looks to be at a different location than where it really is in that. And so Einstein's prediction was for a bending that was about double, 1.75 arc seconds at the radius of the sun, compared to Newton's, which was at 0.87 arc seconds. So a significant difference between those two models that should be easily tested in a solar eclipse. Erwin Finley Friedrich, which was from Berlin in Germany, reviewed all the previous Lick observations and really couldn't resolve any stars to the point to get meaningful measurements. And so that meant, now that we're into 1912 and 13, it's time to look for another good eclipse. And so they pointed towards the 1914 eclipse in August of 14, and William Wallace Campbell, who was from the Lick Observatory, went to Brovary, and Erwin Finley Friedrich from the Berlin Observatory went to Crimea. Both those locations are inside modern-day Ukraine, and that's where they were going to go to observe the eclipse. And the reason for that was, here's the path. What we show here is the path of totality passing across Eastern Europe. That GE balloon there is saying when it was the greatest extent for the duration, but the Ukraine being just south of that was a nice location to be, and Bovary is real close to Kiev, and Crimea is just to the south. Here's a little bit of a expansion of it to see the eclipse path, and Kiev is up in the upper left there, and just below it is Bovary. And so it was going to be a great place to watch the eclipse, and we're going to have a wonderful time there in August of 1914. And Lick built this wonderful set of multiple telescopes to observe the eclipse simultaneously, this array of actually about 7 different instruments, all pointing at the sun at the same time. And they called it the Einstein camera because they anticipated being able to test Einstein's work. Okay. And then June 28th came, 1914, and that's when World War I started. And as a result, the German observers who were down there in Crimea were captured by the Russian troops and were treated as spies. The American team was allowed to stay there near Kiev, but it was cloudy. But as the Americans tried to leave Kiev, and that's the group from Lick, their equipment was confiscated, taken to St. Petersburg, and remained there until after World War I finished. So there were no results, no data that was taken for the 1914 eclipse. In 1915, Einstein made some corrections to his paper, and that led to a slightly refined version with the numbers I showed you previously about the amount of bending of starlight that we'd expect. And that set the stage for the fact that general relativity explained Mercury's precession moving because Mercury was so close to the sun that the warped space-time caused that shift in its near point to the sun, its perihelion point. So the question was, is there actually the bending of starlight? In general, in physics, we like to have a theory that explains what we've seen before and then makes predictions that haven't been tested. And so that's what they wanted to test out. In 1918, the Lick Observatory went just up the road from California to Washington State to take pictures of the eclipse. But remember, their good equipment was in Russia, and the equipment they had just didn't give them satisfactory results. We'll see in a few minutes the challenge of looking at slides to figure out the bending of this starlight as we work through there. So the 1919 eclipse is going to be a great test. It was going to last almost 7 minutes at the greatest extent, but that's out in the Atlantic Ocean, it turns out. It was also passing in front of a collection of stars, what we call the Hyades. That's in Taurus the Bull. So there are going to be a lot of stars near the sun that, in principle, could be measured and give some chance to get some good data out of the eclipse. And the United Kingdom was very active about it, very concerned about it. They had a group they called the Joint Permanent Eclipse Committee, and they planned 2 expeditions for the 1919 event. They were looking for 3 possible outcomes. Either light doesn't bend, or it obeys Newton, or it obeys Einstein. That was what they were considering, and that was the prospects to be checked out. Okay? And the Astronomer Royal from Greenwich, Frank Dyson, was one of the 2 that went, and Arthur Eddington from Cambridge was the other. Actually, Dyson stayed in England and coordinated the work of his subordinates on their part of the trip. And here's the path. And it's a very intriguing total eclipse path because you'll notice the greatest extent's out in the middle of the Atlantic Ocean. But it's very favorable in Brazil in the morning and over as you approach the coast of Africa in the late afternoon. And so the British decided to send one group into Brazil and another group just off the coast of Africa. There's actually a contact point on the coast they could have picked, but they opted to go to an island that was a little bit more centrally located and they thought better weather. So the Dyson team, like it's just of his associates, Davidson and Crommelin, plus the Brazilian national astronomer, Moraes, they were set up in Sobral, which is very, very close to the central line there in northeast Brazil, an excellent place to observe. And they had this wonderful set of equipment. Just to understand what you see here in the photographs, the telescopes remained horizontal, and then there were mirrors that were aimed up at the sun and reflected the light down the telescope. And so they had the 2 instruments set up, and they were going to be able to track the sun. They were on a racetrack, horse racetrack in Sobral to do their work there. The other group was done at an island that's so small that it's really not visible on the map. The marker there is bigger than it's called Principe. But you'll also notice up in the upper left near San Pedro, there was a point, a cape, that was actually inside the path of totality. But the British thought the cloud cover predictions for there were not as favorable as out there on the island, so they decided to go to the island and be out in the middle of the eastern Atlantic Ocean. Sort of an irony compared to our own experiences with the eclipse, where in Indiana here we weren't considered to be very likely as an eclipse location, but we did have a very successful time here, and places that were supposed to be very clear, particularly to the southwest of us, struggled to see the eclipse. So long-term weather forecasting averaging does not necessarily tell you the best bet, and that's just a caution. If you ever go to chase an eclipse again, you got to watch out because you might just get clouds when you get there. And so Eddington from Cambridge took his team to Principe to set up their instruments there. Okay. Here's kind of a in-the-weeds detail that's showing the two different types of telescope frames. The light was recorded on glass plates. Okay. Most photographs, even up to fairly recently, were still done that way. And so we have the difference between the two types of telescopes that were set up to observe. The circle there in the center is the sun. The P is where the sun's center literally was when it was the totality was at Principe, and the S is where it was when it was at Sobral. And you'll see about a dozen or so, number 13 I think is the total number of stars that they anticipated seeing between the two plates. And so that was their goal, to try to record images of those stars during the totality, and then contrast it with pictures taken of the same part of the sky when the sun was not in between, some other time of the year when the sun was far away from that. And so that was our goal, to look for that bending. And this was the idea of the data they got from those 13 stars, labeled by their names. And they're getting into just the slight deviation. These are seconds of arc. Okay? If you think about a circle that's 360 degrees, each degree is made up of 60 minutes. Each minute is made up of 60 arc seconds, and we're talking about 1 arc second of measurement, so 1/3600th of a degree. Not much of a displacement there, but they had their data that they could work from that. And Sobral, the primary telescope, overheated. They forgot that the sun's bright and it sends a lot of light down the telescope. And so that left them just with the smaller telescope for their images. At Principe, remember they went there because the weather's supposed to be better. It was bad almost the whole time. And as a result, they didn't get but a couple of slides that had usable star data on them. And just think about the logistics. Reflecting on our experience here with the Eclipse, we were very busy just keeping the crowd aware of what was going on and kind of observing the whole effect. Trying to take data during a solar eclipse requires, I think it requires dedication that I'm not sure I ever would have to actually accomplish that fact. But here is the best image, actually reproduced in the 1970s by some scientists, of the totality of the eclipse. This is the one really, really good image from Principe. And it's kind of hard to see in the screen, but there's circles around the various stars that we referred to before in that previous table. And as Avery mentioned earlier, one amazing prominence off of the sun here, and that's, that goes around, what, a sixth, well, not quite a sixth of the orbit, or the circumference. So, it's from here to eternity from our standpoint. The sun would be, our Earth would be a dot, barely visible on these images. But they had those stars that they could work with out of Taurus to try to get their actual data. And when they did that, they had the challenge of, when they looked at the plate, this is what that star dot looked like when they zoomed in to see it. So they had to figure out where the center of that star was and how far it moved. And so the red arrow is amazingly the amount of motion between looking at the image when it was stationary versus when it was actually bent by the star. And so some of us might think that was wishful thinking to say it had moved at all, but that's what they came up with. And that was a little bit of the pushback that came from the scientific community after the event. But here was the data. When they finally presented the data for publication, remember there were 13 stars to begin with. Okay. They show the data for 7 stars. Okay, that's because the 13 stars that they saw, they couldn't get good comparison between the two images. The corona actually got in the way of a couple of them. And so those blue circles are supposed to be, are the data based on how much the displacement was, that's the vertical axis, versus how close they are to the sun. And keep in mind here, once again, closer to the sun is to the right on this figure, further away is to the left. So more bend as you get in closer. And there are 3 lines on the data. One is the prediction of Newton, down in the lower right. The magenta colored one is Einstein's prediction. And then the light blue line is the data the line you'd actually get if you tried to fit that data with a straight line from their actual stars. And the simple answer is the work from Eddington and Dyson wound up giving us a bending that was actually even a little bigger than what Einstein said, but within reasonable error if we put error bars on it. And so it did appear that the starlight was indeed bent. Those results were shared in November of 1919, and then they were confirmed more completely by the total eclipse in 1922 that I mentioned, but will lie, when the LIC group went out and did their measurements. They had over 150 stars in their fields that day that they were able to get. And by watching other eclipses through the 1920s and even beginning to pay attention to some stars that are just visible if you make artificial eclipses, if you block the sunlight and record data, which we did on the Earth. By 1930, they had 3,000 stars observed that still showed the basic idea that the starlight is bent by the sun, and general relativity is a good idea. It's kind of difficult to get good results. The 2017 eclipse, we've talked quite about today across the United States, there were 12 sites set up to observe. Almost all 12 of them had the opportunity to get pictures from the eclipse, but only 2 of them gave us data that was meaningful and significant, even a century later in terms of technology. And so that leads to the question, there was data being collected back in April. I've seen no results yet in the media or in the now instant world of Instagram and Twitter postings of anybody having results that confirm it once again. But it was fun just to watch it. I agree with Professor Pasikoff that Avery referred to, that having been to partial eclipses, I even went to an annular eclipse 40 years ago, and it was nothing like seeing the totality. So I leave you with a quote from Eddington. This was sort of in a celebratory dinner that they had a year later. "Oh, leave the wise our measures to collate. One thing at least is certain, light has weight. One thing is certain, and the rest debate. Light rays, when near the sun, do not go straight." Thanks, and I hope you all have a wonderful weekend here back on campus.